All right, and we're going to see two reaction categories that we've seen before, substitution and elimination, but then also one new one called oxidation. All right, so again, we're talking about reactions of alcohols. Okay. And again, we're going to have some familiar classes of reactions here as well as some new ones, but let's just think. So alcohols, like alkyl halides, can undergo substitution reactions. All right. So let's say that I have my alcohol, right? It's got that hydroxyl group on there. Okay, so if I'm going to be substituting it, we're just going to leave this as a variable for right now. If there's going to be a substitution reaction, what do we think my product is going to be? Everybody take a second and see if they can't remember by substitution reaction what we think is going to happen here. What do we do with substitution reactions? Swap our functional groups, right? So in this case, my substitution means that hydroxyl group is going to be replaced by whatever it is we're substituting on there. Okay, so just remember we talked about substitution reactions last chapter as well. Same idea, you're just swapping your functional groups. Okay, so our actual our actual reagents that we use, we're going to see a few of them here, but one of them, the cheapest one, would be simply hydrochloric acid. Okay. And what this is going to do is similar to what we saw before, right? We have this neutral compound here, our neutral nucleophile. Going to be substituted for that OH group, just the Cl, right? So if we were good, we can sort of do our balanced. My other product would be water, but of course the only one I'm really interested in is this organic one here, right? But we can actually substitute our hydroxyl group on our alcohol for a halogen using these, what are they, hydrohalide acids. All right, which is kind of cool because we also know how to go the other way, right? We know how to turn a alkyl halide into an alcohol using something like sodium hydroxide. Okay, so we can actually interconvert these two. But again, for the alcohols chapter, what we're interested in is this one here, our new substitution reaction for alcohols. All right, so then what do you think if I took, let's say, this alcohol and I treated it with HBr? What do we think our products would be? Yep. Same idea, right? Again, we're going to have this substitution reaction. It's just instead of chlorine, we're going to be sticking a bromine on there. Okay. So take a second and draw out our product. Remember, the drawing of the products is really important here, making sure that we have the correct number of carbons, our functional groups in the right place, all that jazz. All right, so then we're just going to put a bromine in place of that hydroxyl group, right? I should still have my same 1, 2, 3 carbons, right? Make sure to count carbons. But these substitution reactions aren't too bad. Again, we're just going to be swapping that hydroxyl group for a halogen. So these right here, these two reactions, and I guess I can be good and put, just to finish it off. Okay. These here, this would be the cheap and easy way to perform these reactions by using, say, hydrochloric acid. Okay. The problem, though, from a practical standpoint, really not an issue with our pencil and paper organic chemistry, but from a practical standpoint in the lab, the problem is that these reactions are, what do I want to say, like, kind of like trying to kill a fly on the wall with a shotgun kind of deal, like really kind of overkill in terms of like the sort of, what's the word that I'm looking for? Anyways, there's a lot of side reactions, unwanted side reactions that occur with this method. Okay, so because of that, we're going to have a set of reagents that we could use that will accomplish the exact same thing. All right, so if I'm, for example, wanting to substitute on a chlorine, I could also use what's called thianochloride, or SOCl2. All right. If I wanted to substitute on a bromine, we also have another alternative that we can use, phosphorus tribromide, PBr3. All right, so again, these accomplish the exact same goal in terms of turning our substrates into products here, the same products. In terms of our pencil and paper organic chemistry, there's really not any sort of difference between the two. It's from a practical standpoint here. These two reagents are much more expensive, but also much more selective. So there's no side reactions. All right, so the bottom line is we want to throw these two reagents, HCl and SOCl2, kind of into the same bin in our mind because they're accomplishing the same thing here. They're converting an alcohol into an alkyl halide using that substitution type reaction. Okay, same thing with the HBr and PBr3. They're accomplishing the same goal there, converting an alcohol into an alkyl halide. In this case, replacing that hydroxyl group with a bromine.
So would you say they're playing the function of alcohol?
Say it again?
Would you say that they're playing the function of an alcohol?
Right.
Like, I don't know if because actually the HBr, it's playing the same function.
So it is very similar to what we learned about our neutral nucleophiles in the last chapter, where you're replacing this group with this, except you're losing the hydrogen in the process. So very much so an analogy with what we saw with our neutral nucleophiles last class. They are actually, we're not going to go into mechanisms, but if you looked at the mechanism, they would be very similar to what we saw. And again, we kind of see that we could reverse these reactions also. We have some reagents to do that, right? So it turns out that these are fairly what are called like a dynamic equilibrium, where just by sort of changing our reaction conditions, we can tune the reaction to go one way or the other. All right, the other one that we're going to learn about that's familiar to us are we can do elimination reactions with alcohols. Okay, so this is going to be using this strong acid catalyst here. All right, actually, since it's just playing the role of a catalyst, it's not actually consumed in this reaction. I'm going to put it on top of my arrow here so we don't get confused. Okay, so again, this is a catalyst. Importantly, that means it's not consumed in this reaction, right? So I'm not expecting any SO, no sulfurs or oxygens to show up in my product. It's just kind of there spectating everything. Truthfully, although this isn't on your OWL homework, but just to note, this reaction also takes place in the presence of heat. When you do this, you actually like boil your alcohol with your sulfuric acid. All right, and since this is an elimination reaction, we convert our alcohol to what functional group? What do we get at the end of elimination reactions? The double bonds, the alkenes, absolutely, right? So just like we saw with elimination reactions last chapter, when we do an elimination reaction with an alcohol, we convert it to an alkene. All right, and then let's think here. So I'm going to have to use this carbon in my double bond, but I got two that I could possibly form, two alkenes here. So let's take a look. Either the double bond that forms between the green carbon and this orange carbon over here, okay, or that pair of electrons can go to the other side to this blue carbon over here, and that would give me this alkene. All right, so which one do we think is going to be the major product of this reaction? We'll call this one A and this one B. All right, let's take a vote here. Who thinks it should be A? And who thinks it should be B? Absolutely, that more highly substituted alkene. Remember, the more substituted, the more stable. So just like we saw last chapter, when we have our elimination reactions for alcohols, we're going to have that more highly substituted alkene that forms. Okay, so just sort of recycling some same concepts that we learned about last chapter of substitution and elimination reactions, but now we're starting with alcohols. Good news, we don't have any stereochemistry crap to worry about or anything like that, no flipping dashes to wedges or any of that jazz for this particular chapter. We do need to be able to recognize what sort of substrate and reagent combination gives us what product here, right? That's the name of the game for these ones. We don't quite have that same level of complication that we learned about last chapter. But let's just now sort of pick, we just had a page of reactions here, let's see what we can do. So I'm just going to put down a few of these reactions that we just learned about and see if we can't correctly draw our products here. All right, so for this first one here, PBR3, substitution or elimination? Substitution, and I'm gonna be sticking on, right? Context clues from my reagent here. It's going to be a bromine that I put on that molecule. All right, remember to count carbons, 1, 2, 3, 4, 1, 2, 3, 4.
For my peace of mind, where does the other bromines go?
This ends up forming like this weird complex with the OH. So it's like PBr2OH, something like that. I don't honestly remember exactly, but I know the phosphorus like incorporates that oxygen into it and forms a new bond there.
Okay.
All right. And then this one, I think the only trick here is you got to remember that it's playing the role of just a catalyst. You're not going to see that sulfur or oxygen incorporated into your organic molecule at all. This is going to be, instead of a substitution reaction, a elimination reaction, right? And so we're going to get an alkene at the end. Okay. As we've seen before, this bond, this pair of electrons, it can either form a double bond on this side or can form a double bond on this side. All right, and this will be our major product here because this would be the more substituted of the alkenes that could form. Right, and I guess just to sort of draw them next to each other so we can be extra special sure that we can see why that is. Right? These are my two options because, again, the carbon at the base of that leaving group, which is in this case an alcohol, has to be involved in that double bond. If I look at this product here, this would be a tri-substituted because this carbon has one neighbor and this carbon has 2, 3, versus this one, whoops, going all over the place. This one over here, this is just di-substituted, right? Because this carbon has one, and this carbon has one other neighbor. All right? So again, how do we determine that level of substitution? We're going to look on either side of our double bond and count how many carbons those two are bound to. So again, this one was tri. For this one, if I look at either side of that double bond, I count 1, 2 carbons. So this one is di. So again, our more substituted one, that's our major product. That's what we want to draw. HCl is going to be what? Substitution or elimination? Substitution. And so we're going to replace that hydroxyl group, this time with a chlorine. Whoa. All right. And then for this one here, I gave you this alcohol and I gave you the product. And I'm asking which reagent should we use here? Who's got one? HBr or PBr3. All right, now if I told you I wanted to do this as cheaply as possible and I didn't really care about if there's any side reactions, which one of these two would I use? The HBr, way, way cheaper. If I told you that I have to have just this one single product and I'll spend any amount of money to do it, which one are we going to choose? PBr3. Okay.
Will it like specifically say if it wants?
So on your homework, it will give you one or the other, and you just need to be able to spy that they both do the same thing, basically. Okay. Again, for our pencil and paper organic chemistry, there's really no difference between the two. All right. So actually, two more reactions of alcohols here that kind of fall outside of what we learned last chapter. The first one kind of segues in. This would be acid-base reactions of alcohols. Okay, so alcohols, of course, if we draw out our structure here, they have these hydrogens, right? So alcohols can play the role of a base. Can play the role of an acid. And remember, what do acids do? They donate their protons, right? So donate that hydrogen. Okay? The problem is alcohol. I mean, if you've ever worked with an alcohol in a lab versus something like hydrochloric acid, if we spill hydrochloric acid, we got to go through these hoops of neutralizing it before we clean it up. It's this corrosive substance. If you spill a little like isopropyl alcohol on your hand, you are not worried about it at all, right? In fact, that's what we use to clean wounds, right? So alcohols can play the role of an acid, but they are absolute crap acids, all right? They're terrible at it. Okay, so alcohols can play the role of an acid, but they are super weak acids. Which means in order for them to do it, in order for them to donate that proton, they require a super strong base. All right, so I can pop off this hydrogen right here. I can treat this alcohol with a base and remove that hydrogen, but I can't just pick any old base. And in fact, the ones that we are most familiar with, like sodium hydroxide, not gonna cut it. All right, we need to use something that's like super duper next level strong here. So one of the ones that we can use would be what's called an amide ion, nitrogen with a negative charge. Almost like a hydroxide, but using nitrogen instead of oxygen, right? So we have our nitrogen with a negative charge. Okay, and I'm going to draw out this bond explicitly here just to sort of see. This is strong enough. This nitrogen can reach out and grab that hydrogen off of that alcohol. And importantly, that pair of electrons that was in that bond will then jump onto the hydrogen itself, or to the oxygen itself, leaving us with this negatively charged oxygen. right? So again, it will deprotonate that alcohol, remove the proton from that alcohol. And we saw this before, so the other way that you would see this same thing written would be sodium amine, right? And what do we do when we see sodium? We erase it and put that negative sign, okay? On your chapter 6 review, I sort of threw them both on there, okay? And let me just talk about why that is. This negatively charged species, this is what's actually involved in the reaction, right? That's why I told you when you see something like sodium, you're just going to erase it and put that negative charge, because that's what's actually involved in the reaction, okay? But if you go log on to like Sigma Aldrich's website where we buy chemicals from, you can't buy a bottle of just a negatively charged ion. It doesn't work like that, right? It always has a counter ion paired with it. So if you were to go to buy these reagents, or you were to look in the stockroom and look for these reagents, you will always find them paired with that counter ion, right? So even though this is what's actively involved, this is what you end up adding to your reaction mixture. It's just the sodium doesn't do anything but sit there and float around, right? The sodium's just there to watch the game happen, okay? So that's why I want you to get comfortable kind of looking at both, and specifically when you see a sodium, again, you erase it, put a negative sign. Okay. The other one that we can use that would accomplish the same thing let's do ethanol actually. Is what's called a hydride. All right, and so again, you would purchase this as sodium hydride, but what are you going to do when you see that sodium? Erase it and put a negative sign. So this is sort of weird. We're normally used to seeing hydrogens as positively charged ions, but when paired with one of those group 1 metals, they do form negatively charged ions. And again, these are both examples of just ridiculously strong bases. Ridiculously strong. All right, so even though our alcohol is a crap acid, if we do have one of these ridiculously strong bases in there, we can successfully deprotonate it. All right, and then why in the world would I want to do that? Well, remember, we saw these playing a role of a reagent in our past chapter, right? In chapter 6, we would use these negatively charged oxygens to do either substitution or elimination reactions. So for example, if I took this thing right here and I added it to an alkyl halide here, we would be able to use our chart to determine that this is a strong base, strong nucleophile, and since this is a primary alkyl halide, this would undergo a substitution reaction. All right, so anyway, why do we care about these reaction types? Because these deprotonated alcohols, they make really good nucleophiles and really good bases, right? So in terms of like, why would we bother performing this acid-base reaction with an alcohol? It would be to create one of those really good nucleophile strong bases that we learned about last chapter.
So in an acid-base reaction, we're just trying to get a negatively charged ion?
Yeah, that's all it does is deprotonate, pull that hydrogen off of that OH group. That's all that acid-base reaction is. Okay, And then our last ones are oxidations of alcohols. All right, now depending on whether you're, so just real quick, how many people are here because they took the 1A, 1B series?
For Chem?
For Chem? Okay, and the rest of you are 3As? Okay, so depending on which series you took, you would have taken, maybe spent a tiny bit of time or quite a bit of time talking about oxidation numbers of elements. All right, this is very similarly related, but it's kind of a pain in the butt to determine oxidation numbers. The nice thing in organic chemistry, oxidation is a little bit much more simple of a definition because, again, we're restricted to such fewer elements, right? So in organic chemistry, oxidation means creating more carbon-oxygen bonds. Okay, so these are going to be reactions that increase the number of carbon-oxygen bonds. All right, so again, I'm going to start with a alcohol here. All right. We'll look at some specific reagents here in a second. For right now, I'm going to just do this little O in a bracket, which just stands for some oxidation reaction. All right, and what this oxidation reaction is going to do is just take this alcohol and increase the number of carbon-oxygen bonds by turning that carbon-oxygen single bond into a carbon-oxygen double bond. All right, and what did we had a special name for this type of bond. What is that? Carbonyl, right? The carbon-oxygen double bond. So, turns this alcohol group into this carbonyl group here. All right, and this we can actually further oxidize, add one more carbon-oxygen bond to this carbon here. All right, we can't make it a triple bond because oxygen only likes to have two bonds. So we're actually going to stick another oxygen on there. Does anybody remember what we had a special name for when we have a carbonyl with an OH group bound? Yeah, so these are these carboxylic acids. We'll actually spend an entire chapter talking about carboxylic acids. They are the organic acid, okay, carboxylic acid groups here. But yeah, so we can take this alcohol, we can do one set of oxidation to make that carbonyl bond, or we can oxidize it even further to create that carboxylic acid. All right, before we go on, we're gonna have to real quick talk about sort of classification of alcohols, which is something that I think we got won't be too bad because we've learned about it quite a few times. So by that, I mean we can classify alcohols as primary secondary or tertiary alcohols. Remember, we did the same classification with our alkyl halides, primary alkyl halides, secondary alkyl halides, tertiary alkyl halides. And that was important because they had different reactivities. We had that chart that showed us how they differed, right? So alcohols are the same way. If you have a hydroxyl group, it can only be bound to one carbon, right? So for example, a secondary alcohol, it's not that that OH is bound to two carbons. It's the carbon at the base has two neighbors. Same as we saw for our alkyl halides, right? They could only have one bond, so when we classified primary, secondary, tertiary, we were looking at how many carbons they had at the base. So take a second and see if you can't draw me an example of a primary and a tertiary alcohol. Right, so a primary alcohol means it's like sticking off on the very end, right? So something like this would be a primary alcohol. And a tertiary alcohol means it's all sorts of crowded, something like this, right? Where the carbon at the base has 1, 2, 3 neighbors. All right, so going back to our oxidation reactions here, was this alcohol that I started with a primary, a secondary, or a tertiary alcohol? Primary. So primary alcohols, we can oxidize them to that carbonyl group, and then we can even further oxidize them to a carboxylic acid. All right, let's take a look at a secondary alcohol. If I oxidize this, everybody take a second and draw me what you think the product should be. If I oxidize this secondary alcohol, creating more carbon-oxygen bonds. All right, so just like before, I'm going to turn that alcohol into a carbonyl. Okay? But the problem is, if I tried to oxidize this again, I can't just like stick an OH on there, right? That's not going to work. I'd actually have to break a carbon-carbon bond in order to add anything else, which isn't going to happen. So secondary alcohols, we can oxidize them to that carbonyl step, but then we're stuck. It's stuck there, right? We can't further oxidize it to a carboxylic acid. There's just no more room on that carbon. All right, so this was our secondary alcohols. If we take a tertiary alcohol, something like this, and we go to oxidize it. Okay, then we'll get this. Cool? I need everybody's organic chemistry brain to explode a little bit here. What's the problem with this product? We got way too many frickin' bonds going on that carbon, right? So we actually can't, because, right, we would have 1, 2, 3, 4, 5 bonds on our carbon. That is super illegal, right? So tertiary alcohols, they're stuck. They can't be oxidized at all. Okay, so again, a primary alcohol, we can oxidize that to that carbonyl group, and then we can even go one step further, add an additional carbon-oxygen bond, because it's just sticking out on the end there. If we have a secondary alcohol, we can create that carbonyl group, but then we're stuck. We can't oxidize it any further. And if we have a tertiary alcohol, we can't oxidize it at all. It's going to be stuck at that first step, at that tertiary alcohol. All right. So we're going to end it there. So what we'll do next class is we'll replace these with the actual sort of reagents that we would use for those reactions. And then we're just going to spend some time reviewing. All right. So again, our exam is next Wednesday. We'll wrap up probably within the first 10 minutes of the next class, all the new stuff. And then we'll just spend time reviewing this alcohols chapter. On Monday of next week, we'll just reach back to the beginning of this unit and try to review as much as we can in that hour in preparation for the exam. All right? So over the weekend, make sure you put in the time to study and stuff like that. Any one of those homework problems is fair game on the exam, right? So make sure if there's anything you don't understand, you reach out to me and we get that all straightened out. If you're working through problems and you can't figure it out, take a screenshot or a picture and send it to me and we can work through it, all right? All right, cool. Yeah, they should be. You should be able to do them for practice, no? Oh, yeah. If you can't, let me know. But you should be able to, anything that's past due, you should be able to go back and do for practice.
Okay. In future scenarios for like the primary, are we always going to have to draw both?
So we'll learn reactions that go from here to here, and then ones that go directly from here to here. But we'll touch that next class.
Perfect.